This is our second video on optimization. Guidelines for solving optimization problems. First, assign a letter to each variable mentioned in the problem. If appropriate, draw and label a figure. Second, find an expression for the quantity to be optimized. Third, use the conditions given to write the quantity to be optimized as a function f of one variable. Note any restrictions to be placed on the domain of f from physical considerations of the problem. Fourth, optimize the function f over its domain by finding the absolute maximum or minimum depending on the problem. Remember that if the function f to be optimized is continuous on a closed interval, then an absolute maximum and absolute minimum of f are, respectively, the largest and smallest values of f of x on the set composed of the critical numbers of f and the endpoints of the interval. If the domain of f is not a closed interval, then we resort to the graphical or some other method. A man wishes to have a rectangular shaped garden in his backyard. He has 50 feet of fencing with which to enclose the garden. Find the dimensions for the largest garden he can have if he uses all of the fencing. Step 1. Let x and y denote the dimensions in feet of two adjacent sides of the garden, and let A denote its area. A simple diagram of the problem is below. Step 2. The area of the garden, A equals xy, is the quantity to be maximized. Step 3. The perimeter of the rectangle, 2x plus 2y feet, must equal 50 feet. We have the equation 2x plus 2y equals 50 and solve it for y in terms of x. Y equals 25 minus x. When we substitute this into the equation from step 2, we get A equals x times 25 minus x, which is equal to negative x squared plus 25x. Step 4, observe that A is continuous on 0 to 25, closed interval. So the absolute maximum of A must occur at an endpoint of the interval or at one of the critical numbers of A. The derivative of A is A prime equals negative 2x plus 25. And if we set A prime equal to 0, we get negative 2x plus 25 equals 0, which means x equals 12.5. We evaluate A when x equals 0, x equals 12.5, and x equals 25. A equals 0, A of 0 equals 0, A of 12.5 equals 156.25, A of 25 equals 0. The absolute maximum value of the function f is 156.25. When x equals 12.5, y equals 25 minus 12.5, which is equal to 12.5. So the garden of maximum area is a square with sides of length 12.5 feet. By cutting away identical squares from each corner of a rectangular piece of cardboard and folding up the resulting flaps, the cardboard may be turned into an open box. If the cardboard is 16 inches long and 10 inches wide, find the dimensions of the box that will yield the maximum volume. Step 1. Let x denote the length in inches of one side of each of the identical squares to be cut out of the cardboard, and let v denote the volume of the resulting box. A diagram is below. The dimensions of the box are 16 minus 2x inches by 10 minus 2x inches by x inches. Its volume in cubic inches is v equals 16 minus 2x times 10 minus 2x times x, which is equal to 4 times x cubed minus 13x squared plus 40x. And this volume is the quantity to be maximized. Since each side of the box must be non-negative, x must satisfy the inequalities x is greater than or equal to 0, 16 minus 2x is greater than or equal to 0, and 10 minus 2x is greater than or equal to 0. This set of inequalities is equivalent to 0 is less than or equal to x is less than or equal to 5. The problem is equivalent to finding the absolute maximum of v equals 4 times x cubed minus 13x squared plus 40x on the closed interval 0 to 5. V is continuous on the closed interval 0 to 5, so the absolute maximum value of f occurs at an endpoint of the interval or at a critical number of the function. Differentiating v prime equals 4 times 3x squared minus 26x plus 40, which is equal to 4 times 3x minus 20 times x minus 2. Setting v prime equals 0, we obtain x equals 20 over 3, or x equals 2. Since 20 over 3 is greater than 5, the only critical number of the function is x equals 2. We evaluate v for x equals 0, x equals 2, and x equals 5. V of 0 equals 0, v of 2 equals 144, and v of 5 equals 0. The volume of the box is maximized by taking x equals 2. The dimensions of the box are 11 inches by 6 inches by 2 inches, and the volume is 144 cubic inches. 11 inches by 6 inches times 2 inches doesn't make sense. That should be 12 inches by 6 inches by 2 inches. Sorry about that. Betty Moore Company requires that its corned beef hash containers have a capacity of 54 cubic inches, have the shape of a right circular cylinder, and be made of aluminum. Determine the radius and height of the container that requires the least amount of metal. Let the radius and height of the container be r and h inches, respectively, and let S denote the surface area of the container. A diagram is below. The amount of aluminum used to construct the container is given by the total surface area of the cylinder. The area of the base and the top of the cylinder are each pi r squared square inches, and the area of the side is 2 pi rh square inches. So S equals 2 pi r squared plus 2 pi rh is the quantity to be minimized. The requirement that the volume of the container be 54 cubic inches implies that pi r squared h equals 54. Solving this equation for h, we get h equals 54 over pi r squared. We substitute this into our equation for the surface area and get the equation S of r equals 2 pi r squared plus 2 pi r times 54 over pi r squared, which simplifies to 2 pi r squared plus 108 over r. The radius r of the container must satisfy the inequality r is greater than 0. The problem is reduced to finding the absolute minimum of the function s equals f of r on the interval 0 to infinity, which is of course an open interval. Step 4, to find the critical number of s, we compute s prime equals 4 pi r minus 108 over r squared and solve s prime equals 0 for r, giving us r equals 3 over the cube root of pi, which is approximately 2. We next show that this value of r gives the absolute minimum of r. We first compute s double prime equals 4 pi plus 216 over r cubed. Since s double prime is greater than 0 for r equals 3 over the cube root of pi, the second derivative test implies that there is a relative minimum at r equals 3 over the cube root of pi. This relative minimum of s is also the absolute minimum of s, since the graph of the function is always concave up, since s double prime is greater than 0 for all r greater than 0. To find the height of the container, we substitute 3 over cube root of pi into our equation for h to get h equals 6 over the cube root of pi. We conclude that the required container has a radius of approximately 2 inches and a height of approximately 4 inches, or twice the size of the radius.